All right, here we go. So just to summarize, we're maximizing the area of a single pen. We got this equation. We can't do derivatives of two variables, so we use our constraint. Here there's 2,000 meters of fencing. And now let's make this an equation of one variable. So a as a function of x is x times 250 minus 0.625x. This is just a quadratic function that opens down. You could have done this question in grade 10, find the vertex. We are kind of finding the vertex using calculus techniques. Now, I do want to, I know you guys are smart, and so we know that this really, you don't have to copy this down. We know that if you were to graph this function, it'd be a quadratic function that opens down, and we know that the maximum area will correspond to the vertex. But I think it'd just be good practice. Let's actually find the domain of this area function. X obviously can't be any number because X represents that physical dimension in our diagram there. So you guys want to have a little think here? What's the domain of our area function? So in other words, could you maybe fill in these blanks here? X is between what number and what number? What do you guys think? Technically, how small could you make X? Technically, so you could make it 0. So you could take a kilometer of fencing, line it up, take another kilometer of fencing, line it up side by side. Technically, you could do that. Is that a good area for the horses? No, but you technically could do it. So the smallest X can be is 0. Did anyone do the math? How big X can be? So there's 5 of them, and we have 2,000 meters of fencing. Yeah, 400, yes. 400 meters. Yeah, if X was 400, well, then you'd be just lining up a 400-meter section of fence side by side 5 times. Technically, you could do it. Is it a good idea? No, but that's what the domain of our area function is. So let's go about finding the derivative, setting to 0, and finding our max. Last week, and in general, we usually kind of expand these out. When you were back in grade 10, maybe you left it in factors form to find the vertex. Maybe you expanded, then completed the square. Nobody likes doing that, though. So we'll use the derivative. What is it? 250 minus 2 times 0.625 is 1.25 times x. And we set that to 0 because we know that the maximum occurs at either the critical points or the endpoints. Endpoints are kind of silly here. So really, we just need to find the value of x that makes this derivative 0. So let's solve that little equation. Put the minus 250 on the other side. Should work out nice. Looks like 200. Nod and smile if you got 200 as well. Let's see some nods. 200 meters. Okay, so we're basically done here, guys. This was a quadratic function that opens down. The smallest x can be is 0. The highest it can be is 400. And we got x is halfway between. It's 200. That's going to correspond to our vertex. So we're done. We don't really need to check any endpoints here. Let's just wrap this up. The question did say determine the dimensions of a single pen. So if x is 200, what's the y dimension? We have that at the right. Y is 250 minus 0.625 of whatever x is, 200. 5/8 of 200. 125. 75? No, not 75. 125. 0.625 times 200. 125? 125. All right, let's wrap this up. Maybe off to the side here, the dimensions of a single pen should be 200 meters by 125 meters. And then maybe if you wanted to, give your rancher friend an idea of what that would look like. 1, 2, 3, 4. That means the whole thing would be 500 meters, each individual one, 125, and then vertically 200 meters. So it'd be, the whole thing would take up 200 meters by 500 meters of space. Hope you guys would agree. This is kind of similar to the beach question from Friday. Not much different in terms of the math. Setting up was a little different, but for grade 12 calculus students, I wouldn't feel bad giving this to you guys. I don't think that's too bad to set up. And like any question that was kind of the same, like, I don't know, like if it was 2 rows of 2, you could just do the same thing. Count up all the X's, count up all the Y's. 2 rows of 2 rows of 5 pens. Like they'd all be the same question, right? Just literally all the same question. Just the numbers would change a bit. Okay. Anything you guys want to chat about with that one? All right. Let's try revisiting a classic from grade 10. These kind of like maximizing revenue questions. But we'll do it from a calculus perspective. We'll also add in a little constraint here that makes us check the domain. But yeah, you guys could have done this question in grade 10. We're just going to do it using calculus techniques. But this is actually a useful question. So here we have a train. Currently, we have 2,000 passengers, and the cost is $7 per person. But like many things, if you increase the price, less people will buy or use your service. If you decrease the price, more people will buy your product or use your service. But somewhere in the middle, there's probably like a best price to charge, so you maximize how much money you're taking in. So that's what we're going to find here. The only twist with this one is that the capacity of the train is 2,600 people. And we don't want to carry less than 1,600 passengers because here the reason is costs exceed revenue. So we have to make sure that the answer we get using calculus doesn't go outside of those boundaries. Like, what's the point in reducing the price so that 3,000 people want to use the train when you can't actually fit them on anyway, right? So let's begin. When you guys were in grade 10, with these kind of questions, to make your equation for the revenue, we always start with this. So I'm going to use X, but the independent variable we use represents how many times we're increasing the cost. So we'll let X represent the number of 10-cent increases. And now we want to make an equation for our revenue. So same process as before. So let's just start out with, so how do we get revenue? Revenue is a fancy word for how much money you make. And it's the price times the number, I'll just say number sold. I'm not a business guy, so I don't know the technical term. That's basically it, right? It's the ticket cost times how many passengers there are. And we can get an expression for that in terms of X. So we can create a revenue function, R of X. So what's an expression for the price? Well, the price was $7. And every time we increase it, we're adding 0.1 on. So if you just think about this expression for the price, it makes perfect sense. X equals 0, do nothing, price is 7. X equals 1, you increase it one time, it's now 7.10. X can also be -1. You could decrease the price by 1 if you want. That would give you a price of $6.90. And then an expression for the number of tickets sold. Well, we currently have 2,000 passengers, and for every increase of 10 cents, we lose 40 people. So we would have minus 40 times X. So increase the price one time, we now have 1,960 passengers. But if you decrease it one time, if X is -1, then you have 40 more passengers, because -40 times -1, positive 40. You guys okay with that setup? You do those kind of questions in grade 10. At least when I teach the grade 10 academic course, we mix those in when we do finding vertex and stuff like that. But we have a twist in this one where X can't be just anything. Like in theory, you could increase the price as many times as you want, up until like $1 billion. But no, like we have some constraints on how the number of passengers. So we got to find the domain of this function. I think I'm going to do that. Miss Plattner would not be happy with me. I'm going to maybe just split my page in half here. And on the right, let's talk about domain is DO. I know that. Let's talk about the domain of our revenue function. So let's talk about first, okay, the capacity is 2,600. So what value for X, how many increases, in this case is decreases, get us to that capacity? Because like after that, we won't want to decrease the price anymore, right? There's no point. Let's find it out. The expression for the amount of tickets we sell, or the number of passengers, is 2,000 minus 40x. And we're going to set that 2,000 has a 0. We're going to set that equal to 2,600. Can you guys solve that equation for X? And then we'll know how many times we can decrease the price by. Minus 4x equals 2,600 minus 2,000. That's 600. That is... Oh, okay. That's okay. I caught it. You guys, again, you can tell me when I do something wrong. It's 40x. I put 4x, right? Yeah, 40 is not equal to 4. You guys. There we go. So that gives us a more reasonable answer. -15. Okay, so what's that tell us? Don't decrease more than 15 times. Okay. So can you guys do the same thing? So we have a minimum amount of passengers. Passengers is 1,600. Can you guys do the same thing and find out what value for X gives you 1,600 passengers? And then we'll know not to increase the price more than that. $2,000 minus 40x equals 1,600. minus 40x. 1600 minus 2000, that's minus 400. You guys get 10? All right, if you increase the price more than 10 times, then you're below that minimum threshold for passengers. So we don't want to increase more than, don't increase more than 10 times. So in conclusion, we've got our domain function. So I'll use this notation just to mix it up. So what can x be? Well, x has to be between minus 15 and 10. We can't decrease the price more than 15 times. We can't increase it more than 10. So our best value for x that gives us the max revenue, somewhere in there. So let's go back to our function and let's find the vertex. In this case, it's quadratic again. But let's find find that critical point, find that vertex, and then we'll see if it's in that domain or if not. You can find the derivative now if you want, but I think I'll put it in, I'll expand it out. I'm not your dad though, do whatever you want. We'll get the same answer. So let's use some FOIL, 14,000. 7 times negative 40 is minus 280. 0.1x times 2000 is 200x. And 0.1 times negative 40 is negative 4, and that would be x squared. I'll rewrite it with the highest power first. It's negative 4x squared minus 80x plus 14,000. I'm going to double check because you guys don't tell me if I do stuff wrong. I think that looks okay. All right, can you guys go about your business? Take the derivative, set to 0, solve. We're looking for a value between negative 15 and 10. If we don't, then the best value will be actually minus 15 or 10. It'll be one of the endpoints. Minus 8x minus 80. Set that to 0. Minus 8x equals 80. Guys, at x equals negative 10. All right, we're basically done. So what does that mean? X equals negative 10 means decrease the price 10 times. And it's inside our domain too, which means that's the vertex of our quadratic function. We don't really need to check any endpoints here. We can just actually wrap this question up. Question asks for what fare should we charge? So what price should we charge? Well, what price is this if we decrease the price 10 times? I'll show the math here. We said that a price was 7 plus 0.1 times whatever x is. X is minus 10. I mean, you guys could have done that with mental math. If you decrease the price 10 cents 10 times, the price is $6. So $6 per ticket. They'd make a bit less per ticket, but they'd get way more passengers, and that's the happy medium there. Again, nothing crazy new today, just applying stuff we know, just broadening your horizons. And you guys probably have done questions like that before. Do you guys want to chat about anything with this one? So we've done a variety of measurement problems, 2D and 3D now. We've done a revenue problem. And I can tell you guys, when you guys do your test on Thursday, I'm not going to give you something crazy different than something we did in class, okay? Or like the practice, but the practice is like the stuff we do in class as well. All right, that's it. That was the lesson. It's only 9:11, but we're all done. So let's talk about marching orders. So you guys have a bunch of practice. It's the same document as last week. So don't need to re-hand out anything to you guys. It's just a few more questions. I will, after I take attendance, I'll get the review stuff printed off, and I'll just give that out to you guys now as well. And then you guys can just choose on what you want to work on. Arguably, we have like over 2.5 days of just class time to like practice, because I would say today wasn't really any new stuff. Um, I'll let you guys get to it. Let's use our time well. Remember, we'll be like Rock Lee and be geniuses of hard work.